All right. Welcome everybody again. Any point to touch from our last discussion before moving on to the next ones?
I'm good.
Wonderful. Yeah. Miles.
The presentation is ready for next week. Same time.
Yeah, sure. And if you want me to look over, I'm happy to do that as well.
Okay.
All right. So today, again, probably we have covered a major portion of the T-ray based imaging, spectroscopy, and several other topics like kinetics, diffusion, real-time diffusion measurement, thickness profiling, etc., as well as reaction kinetics. Today, we're gonna talk about the photonic crystal-based sensor and application. And that's the last topic, as well as we thought we could touch on T-ray based Raman spectroscopy. So we still may want to do that. First, let me share my screen. And so maybe I should go to the presentation mode from here. Okay. So photonic crystals and sensors. The motivation of this work was to create a sensor which will be powered by terahertz or T-ray, but for rapid detection of things that are important in the biomedical and medical industry. So what is a photonic crystal? They are periodic structure made of dielectric materials that interact with resonance with radiation at wavelengths consistent with the periodicity of the lattice network. So in simple words, photonic crystals are man-made lattice. As you know, crystals are made of lattice, atoms that are positioned in particular design or particular places. Those places are called lattice in the crystal. But nature-made crystals have a lot of defects in them. In other words, nature loves defect. One wouldn't find any nature-made thing that doesn't have some kind of defect or another. So it was always of interest to find a way to create lattice so that we can manipulate things in a controlled way. And that is the gist of this photonic crystal. It's also called metamaterial, the same thing. It's also called band gap structure. So, the advantage of having a man-made lattice is that you can control the band gap, you can control the periodicity, and in doing all of those things, one can control the functionality for sensing, for many, many other things. But here we are going to talk about sensing. So photonic crystals are designed to confine, manipulate, and control the propagation of photons. In other words, lights, but we have applied it for T-ray as well. So this is some of the examples of different way of photonic crystals are made. They can be pillars, they can be holes, they can be network, rods, and so on and so forth. So there are a lot of information available. You can look it up. We particularly were interested in application of the photonic crystal, not so much for design of it, but its application for our purposes. So here it says that the major characteristics of synthetic photonic crystal is dielectric networks, retain connectivity. The active elements have the same average optical path, high ratio of dielectric indices. These are none of these are set in stone. A lot of people design their own way. And that's where the meta-atom and metamaterial jargon come from. So let me go to our PBG, or photonic band gap, range in wavelength within which there is no absorption or propagation of light by a material. The PBG is a wavelength range in 3D dielectric structure. I mean, I have copied this from a textbook, so you can, look it up. When I was teaching a course, I don't teach that right now, so much busy with all other things, but this is that particular course that I've taken from. And these lines are the goal of photonic crystals is to exclude light transmission in all directions for specific wavelengths. The PBG is determined by the radius of the holes. So this is a hole-based ones. As I said, there can be pillar-based ones as well, and there can be array-based ones. So the hole-based ones, the radius of the holes determines the transmission characteristic. The periodicity of the holes also another factor. The lattice structure, the thickness of the material, and the refractive index. So these are the main determining factors. The most important thing to understand here is that the structures are made lithographically. So as long as the design is within the lithographic, ability for the lithography to handle the structure, that can be made in the fab, and then sensors and other things, optical splitter, optical combiner, many other things can be done. So here is a specific example that I'm going to talk here today. What we have done here is taken what they call as a nanoporous lumina membrane. So here's a company we worked based in Colorado. They make this particular photonic crystal. This disc, this is a alumina membrane. They start actually from aluminum foil, then do some chemistry on it, and eventually this kind of regular holes are done in that structure. The hole under microscope, this is an SEM image. So they section it vertically, along somewhere along this line, so that they can expose the propagation of the hole from one surface to the other surface, and how the holes are organized across the thickness. This is the image that came from the manufacturer of this photonic crystal or disk. So these two images are from them. So what we did is made a disk holder, as you can see here. So it's a piece of plexiglass where we made a hole, and one side of that hole we mounted this disk, photonic crystal disk, with the glue in a way that glue are applied in the peripheral areas so that it does not hurt or interfere the hole itself, because in that hole we are going to put the samples. And so this is a sensor now. So the principles are explained in the next pictures. Basically what happens is that if you take this blank one, then it has a frequency characteristic. And we are talking about here eigenfrequency analysis, as we described before. But then when some molecules are attached on the blank, there is a shift. And we have defined these three quantities: shift of the main peak, shift of the secondary peak, and also the difference between the loss factor. The absorbance is the loss, right? So we define delta 1, delta 2, and delta 3 to be able to identify this material here. So first we apply in the mini cuvette that we just formed. Then we have applied in this case, a oligonucleotide solution in a buffer, because where am I going to get the virus to do the experiment? We need a specialized lab for that, which we don't have. So instead of virus or pathogen, we wanted to provide a proof of concept with this benign oligonucleotide experiment. So when this is a room temperature drying of the buffer. So at this point, as you can see, the buffer has dried, only the oligo remains on the photonic crystal sensor. And then we take the spectrum. And when we take the spectrum, we did the eigenfrequency analysis, and we see this kind of peaks. Compared to the blank, the oligo has made some change. So now we can define the delta 1, and we can measure. Not only we defined before, now we can measure delta 1, delta 2, and the difference of the loss factors is the delta 3. With these three parameters, we can now find a way to identify the species that has been adsorbed. So combined plot of the eigenspectrum of blank G oligo, meaning that this is only a guanine oligo, nothing else in there. The loss factor difference at saturation is measured with in decibel, and the difference in the peak frequencies are, of course, in terahertz or hertz. So once these three factors are known, then we apply them in the following way, formulating a criteria for identification. The three eigenparameters, delta 1, delta 2, and delta 3 are defined and measured, of course, where delta 1 corresponds to the mass parameter of the species that is adsorbed on the sensor, and delta 2 corresponds to the size parameter, and delta 3 corresponds to the effective charge parameter, which is causing the loss. Since the mathematical expression, so the mathematical expression of this computation algorithm is very well known and are in those references. This is actually published in a paper, so I don't know if I remember to share that paper with you all, but if not, I will do so. So the measurement technique has been emphasized for the detection application of the algorithm. So in a nutshell, I don't have a lot here. Maybe I should show you that paper, or I once I send you the paper, and if you have any question, you're welcome to ask. So the formal presentation is ended here, and I have been too occupied to make a slide for this Rahman spectroscopy application with T-ray, or as they call it, a T-ray Rahman. So T-ray Rahman is, as you know, the Rahman effect is the main thing. It's similar to what we have just shown you in the T-ray photonic crystal sensor, except in case of Rahman, it's only one peak shift. That's what is utilized. So here, this paper has not been published yet. We're still working on it. If anyone wants to volunteer to finish it, you're welcome to do so. But what we have discussed here is what advantages and limitations of Raman spectroscopy. So this is just a literature survey. And then we talk about the limitations. Why Raman is a very successful technique for molecular identification, and yet it has quite a few limitations. These are all from the literature survey. And then how does T-ray spectroscopy go about doing the Raman detection, and what kind of improvement it brings on? We have discussed that. And in Raman, then there are also the Stokes lines and anti-Stokes lines with respect to the reference. In T-ray, the difficult part in T-ray is that when you do regular Raman, you have a single wavelength laser as the reference line or excitation line. In case of T-ray, as you have seen in the T-ray spectrum, it's a broadband spectrum. So there's not a single excitation line. As such, you can have anti-Stokes lines as well as Stokes lines. In regular Raman, they deal only with the Stokes lines. So anti-Stokes lines may be useful in some cases. I haven't seen any, but scientists think that it could be useful as well. So with that, then we summarize the advantages of, then with that, we do some experiments with the endohedral molecule, in particular the carbon-60. You have seen the spectroscopy of this before, but you haven't seen the Raman characteristic of this. That's what I'm showing here today. So the C60, hydrogen impregnated C60 and deuterium impregnated C60. Those are three samples we have studied before. And samples came from Professor Nick Turo, who passed away in 2012. He was my mentor, advisor, postdoc advisor. And he was so kind to share the samples with me when he was still around. And I have yet to publish that paper. So as you can see, how much behind I am with everything in my life, so to speak. So this, you have seen this, how those are done, but here is the experimental details. On a glass slide, we made that, dropped one drop of the solution with C60, as well as H2R-C60 and D2R-C60, other slides. And those slides are placed here in the spectrometer, positioned it with the 3-axis positioner, manual positioner. and then the, you know, I can do that, okay. And then the interferogram was acquired, and then once these 3 interferogram were acquired, then we could do the Raman calculation out of the spectrum. So we calculated the spectrum. These are regular T-ray spectrum and not eigenenergy analysis. This is just regular, you know, absorb. In this case, it's amplitude spectrum as a function of different wave numbers. So where Raman would have been stopped around here for 500 wave number, we have this low frequency region due to T-ray energy. So then, this is a close-up, actually. This is a close-up of this graph showing that the 3 spectrum are different. So now we are ready to calculate the Raman shift. And this is the calculation of the entire spectrum for Raman shift. Raman shift formula is available, so I did not put it here. And then, you know, it shows that beyond about here, 350 or so wave number, there's no more Raman activity going on. So any Raman activity is confined within this region. And that's why we're showing a close-up of this graph up to 350 wave number. And that shows the Raman activity of C60, H2 at C60, and D2 at C60 are quite different. And they're showing in the amplitude spectrum, they're showing different peaks. So that shift is now, with respect to the C60, now we can calculate how the Raman shift is happening. And that then becomes signature of those particular molecules. So here is a summary, comparison of absorbance peaks and amplitude. When C60 itself has these wave numbers, the Raman shift of the H2 at C60 are identified here, but D2 at C60 has a lot more Raman activity compared to H2 at C60, and also compared to just C60 alone. So again, you are welcome to have a copy of this, although it is not a finished paper, but some backgrounds are here. I'm happy to share with you if you ask. I think we came to the end of the workshop here. So next up, we go through the discussion as well today, and then next up is your presentation.
Can you send that paper? This
I will, sure,
paper,
absolutely.
Raman spectroscopy.
Yeah.
I would like to read it.
Both of them I will send it, yeah.
Good. I had a question on your earlier PowerPoint presentation.
Sure, absolutely.
If you can go to that alumina sample or course. Was it aluminum or alumina?
Let me see, share that again. So the photonic crystal, they call it a nanoporous alumina membrane. Although starts with metallic aluminum, but when it is oxidized, it becomes alumina. And then, which is basically Al2O3, aluminum oxide.
Right.
And
anyway, sorry,
yeah.
Go ahead. Finish your thought.
Is this shared?
Yeah, it is that. So the question I have is about the aspect ratio of these holes. I see 2 numbers on the left bottom. One is the uniform array hole is 60 nanometer diameter. And the other one at B, it says pore size 40 nanometer. Can you explain those two numbers and the
Yeah. So
aspect ratio?
sure. Good point. Very good point. So what happened is we got multiple samples from these manufacturers. It's a company in Colorado, as you mentioned. So they asked us what kind of pore size would be good for us, and we didn't know the answer to that. So we eventually decided to do the experiments on 40 nanometer pore size. But these images are for 60 nanometer pore size. This is what they sent to us. So we didn't take this image ourselves. So this is a different, the SEM picture is only showing that this plate over here is a nanoporous plate, and the pores go from one side to other side, and they have this kind of arrangement. But when we did the actual experiment, this is where we have 40 nanometer pores for the actual sensing experiment. Yeah.
But by definition, if you go back to the previous one, the pore size or the diameter is same thing, right? Or different things?
On this one, the diameter, you mean the aspect ratio of the holes?
Yeah, I mean, the diameter of the hole and the depth of the hole, the ratio is called aspect ratio.
Well, the hole goes from one surface to other. So this thing is about 5 micron or so thick, this disc itself.
It's a large aspect ratio.
Yeah, very
large.
Compared to thickness, the holes are really narrow, and that's why it can serve as a meta atom. If the holes are micron, then it would not serve any purpose.
Right. Do you know how did they make it, the holes? Is it some kind of lithography?
No, it's all chemical. It's all wet.
All chemical.
Yeah.
So the uniformity from one side of the hole to the other side is good? Same?
Well, this is what the picture shows. And
right.
Take it. We didn't do anything about that. We took that piece and carried out our thing. It is pretty uniform. In other words, blank sample to blank sample, we always got the same spectrum.
The reason I asked is that by chemical etching or making this kind of pores is usually not that uniform compared to the lithography. Lithographic techniques are relatively a lot more uniform and maintain the hole diameter from one side to the other side uniformly or close to uniformly.
Right. Well, first of all, lithography will not be able to do this. Drilling 5 micron hole in alumina with lithography is impossible. So we even couldn't dig 2 micron.
Mm-hmm.
No, I'm sorry, about 5 micron in our dendrimer. We tried to make waveguide that way. So
yeah, you're right. Usually 100 to 200.
Yeah. So this 5 micron thick disc. They have a pretty good handle on this thing. This company has been around for a while.
Yeah, it's pretty impressive if it is done by chemical.
Yeah. They have figured out the process. The two young Russian American, so to speak, down in Colorado. We still have a very good relationship with them. If I have some of the blank ones still in my lab.
Mm-hmm.
And we can get more. They would sell it to us, so that's not a problem.
Okay, the another question, or my final question, about the Raman shift, maybe 2 or 3 slides down.
No, Raman shift is actually.
Oh, another one, right?
Yeah, it's a file here.
Right.
I did not.
Right here.
Make any slides. Yeah, here.
So there's significant difference, of course, between C60 then.
Mm-hmm.
H2 and D2,
yeah.
D2
Yeah.
But why? So there should be so much difference between H2 and D2. If you look at the enlarged one at the top right, especially the deep on the red one or the H2 one, around 120 web number, I suppose.
Yeah, yeah.
It's a very significant difference. What does that mean between H2 and D2 here?
So H2 is simply one proton.
Right,
D2 is one proton and one neutron.
correct.
And so this is also known as a rotor in a cage, right? C60 molecule is like a soccer ball.
Right.
So they open the top and put the either hydrogen in there or deuterium in there. We were still looking for tritium sample, which we didn't get. But then that one neutron makes it twice heavier. Therefore, the rotational spectrum of hydrogen and deuterium are quite different.
Right.
And it's a rotor in a cage because the molecule cannot, linear vibration, linear translational motion, many other resonances disappear except for rotational resonance. So they have done quite a bit of work, except we have yet to find another similar work to compare. So this could be considered as a novel work. We have yet to publish it, so that's another thing.
Yeah.
I mean, you are welcome to look at it and try to improve and publish.
I would like to.
Okay.
Now here for the peaks or the deep at 120 wave number, if you go down another table you showed,
Here, yeah.
which peaks are representing that delta between D2 and H2 here for that specific location or wave
Delta
number?
has not been calculated. These peaks are just enumerated here. So delta can be calculated, which probably another thing that we need to do.
Okay, thank you.
Absolutely. Miles is thinking very hard today.
Maybe so.
Question?
No questions at the moment.
No one. And Fareen, what do you think? All right. Then if no more question, Dr. Mujum, there any other question before we close?
No, that's fine. Definitely interesting.
Okay. So I will send these files to all of you. And then next week, we have presentation from Miles and Fareen. And then following week from Dr. Majumdar.
So what are the topics from Miles and Fareen? Do you have the topic?
My topic is about a business plan or business proposal to community colleges or universities around the nation. So I made a list of schools in my local area and talk about how to communicate with them, the format, maybe the overall conversation, the flyer. I want a flyer sent to them, those things.
I see. So you are gearing up, at least aspiring to go to academia?
Yeah, I have experience in academics, not with the sale of an instrument to them. So I taught for a while, both high school and college for a moment. But selling an instrument to them is next week's presentation. I want to try to make friends with maybe a lab director or somebody willing to host the labs. start with the head of the department, go to the lab director, maybe that type of thing. It's people sell NMRs to schools, which are humongous.
Yeah.
This should be possible.
Okay, got it. Thank you.
All righty, then let us stop here for today and see you next week.
Yep.
Have a
Thank you,
wonderful
everybody.
weekend, everybody.
Thank you.
Yep. Have a nice weekend.
Bye.
Bye.